In today's episode, Alex will be interviewing Alice Porter, who works in particle physics, and looks at how we can develop the new detectors to look at the smallest particles in our universe.
Hello, thank you very much for joining us. Today we're joined by Alice Porter, who is a final year PhD student studying particle physics, focusing on the detector side mainly.
Yes.
So hello, thank you very much for joining.
Morning. Thank you for having me.
So would you be able to just give us a quick overview of your research before we kind of jump in?
Yes, so I work on 3D diamond detectors. So these are what's known as like an ultra radiation hard type of detector. Well, that means it can just withstand being in really, really radioactive places.
So before we kind of jump into what you're actually researching, would you just be able to kind of give us a brief idea of like what your average day is like, what you what made you kind of decide to do a PhD?
Okay, so it's like two
kind of different questions there, but
So my typical day, I spend a lot of time in a laser lab, which I will talk about in a second. I also spend quite a lot of time doing data analysis and simulation work, and also because I'm part of CERN, I spend a lot of time in meetings with people all across the world. So that tends to segment my day quite a lot. Why I decided to do a PhD. Long story. I thought before I even started university, I think a lot of people have this idea like I'll go and do physics and then I'll become a lecturer and I have to do a PhD to do that, etc. So that's how I started off. I actually originally wanted to do astrophysics, then I got to uni and decided I did not. Probably shouldn't say that in the job function, but yeah. Then during my undergrad, I thought I wanted to do say a coding job, and by the time I got to do my master's project, I really loved it. It was actually doing some proper science, and then came about the time to start doing PhD, and I sort of just went for it. I didn't really know what to apply for. Could even give you a funny story how I didn't actually apply for my PhD.
Oh, okay.
So it was just sort of happen chance. Yeah, but I know I wanted to do something where I could really get my teeth into it, which is a bit more like how a master's practical project would be.
Yeah, I've definitely agree with that because I'm currently doing my master's as well, and I definitely agree. It's kind of a good chance to kind of get your first proper research in there.
Yeah. Oh, a PhD is like doing your master's project but all day, every day.
That's good to know. Now I think we should probably kind of jump into what you're actually doing. So 3D diamond detectors. Diamond.
What is it?
So that sounds like it's quite expensive.
They are expensive, right? My best friend. But so yeah, diamond. Why are we using diamond? So most detectors, particularly solid state detectors, are made out of silicon. So most basic being like a diode that you've come across if you studied undergrad physics. Silicon's very good, and that's where the majority of the field is. But when we're talking about the forefront of particularly high energy physics, we care about radiation tolerance. So how long can you put it in that environment before it starts to break down? And the way that it will break down is if you think about your crystal lattice. So you have the bonds between the atoms, and when it's being bombarded with radiation, sometimes those atoms get displaced and knocked away. So for silicon, it sort of depends on what temperature it's at and how long it's been there. But just from perhaps basic chemistry, you know that diamond's super hard. Mm-hmm. It takes a lot more energy to knock a diamond atom from its crystal lattice than a silicon. That's the very basic reason why we're interested in diamond as a detector.
Okay, interesting. So they kind of just last longer under the high sort of
exactly.
particle.
So, and also, diamond is not only the hardest material in the world, but it also has the highest thermal coefficient, which it means that it will get rid of any heat from electronics or anything, or just from being radiated as fast as you possibly can. So a big problem that silicon detectors have is they have to be cooled in order to be used. Mm-hmm. So you'll find that a lot of, particularly, so I'm going to use the example as LHC, but it's a lot of places, they have huge expansive cooling systems to keep the detectors at a usable temperature, which is usually below 0 degrees Celsius. So that's technologically challenging. Diamond requires no cooling. You can even use it at room temperature or higher. So it has some advantages there if you sort of ignore the price. So yeah.
Okay, that sounds pretty cool. So how big are these diamond detectors? Are we talking?
Yeah, that's another really good point. I'm glad you asked me. So I work specifically with synthetic diamonds. So these are lab-grown diamonds. They're starting to come onto the jewelry market now. You're starting to see adverts for lab-grown diamonds, a process called chemical vapor deposition, so sometimes called CVD diamond. And you can get different sizes of them, but the way the process works, you can get different grades of diamonds. So if you imagine you've ever studied growing crystals, the slower you grow them, the more pure the crystal, a bit like how magma forms, right?
Mhm.
So rocks. So if you want the super single crystal diamond, which is the best diamond you can get and it's completely flat, you're actually quite limited by how much you can grow them. So a single crystal diamond, they tend to be ones you get around 3 by 3 millimeters across. So
Okay.
we're talking like size or smaller than your little fingernail. But then if you want less, so a diamond with more grain boundaries, say it's not a single continuous crystal, you can go bigger, 10 to 15 centimeters.
Okay, so pretty big then.
Yeah, so the biggest ones I think are this big that have been grown, but we tend to use sections of them. So it's an important question to say because the area you can cover when you're measuring something is of a bit of interest. So I tend to work really small areas, which is working at the frontier. So it's a scaling problem, but when I explain my particular research, it'll become clear why I talk about small areas.
Mm-hmm. So do those smaller crystals, the single crystals, do they work more efficiently than the larger ones?
Yes. So if you have a grain boundary or some sort of defect in your lattice, that can trap your charges. So when a detector works, or say you take your gas ionization chamber, it works the same way, but it's just solid. So you have electron hole pairs that from your instant radiation that makes the signal. When those are traveling through your lattice, if there's any defect or grain boundary, that will trap charges and reduce your signal, might make them slower. So, that's a thesis in itself. But yeah, so you're trying to avoid that, right? So if you have a single continuous diamond, a single crystal diamond, you're gonna have the least amount of that, but it's the most expensive and it's the smallest, right?
Okay.
So your polycrystalline diamond or your more defective diamond is bigger and cheaper, and we would like to use that more often.
Okay, that's very cool. So, like, how do you actually read out the measurements from these diamonds? Do you have to have like wires in them somehow?
Yeah, well, this is exactly what I work on. So your, I'll say conventional, traditional detector looks like a sandwich, right? Mm-hmm. So say you're playing silicon or parallel plate capacitor, you may have studied. Looks a bit like a sandwich. We've got 2 electrodes and your piece of solid in the middle. Mm-hmm. So you can do that in diamond as well. We call those planar diamond detectors. And that way you just deposit metal or some conductor either side of the diamond and you have your parallel plate capacitor. I work on 3D diamond. What the 3D is describing is instead of having your electrodes as your sort of piece of bread in a sandwich, we instead make them columns and they're inside of the diamond. So if you imagine perpendicular to the surface, like you're putting rods inside of it.
Okay, so like little tubes go through the diamond itself.
Yes, exactly. The wires going all the way through the diamond. This was first done in silicon, but the way that silicon is, you have to do a lot of processes. It's very involved in sort of solid state physics and electrical engineering and sculpting your doping profiles, etc. Diamond, as you're probably familiar with, is transparent. It's shiny. It's see-through. Yeah. So I mentioned I work in a laser lab. What I'm doing in the laser lab is focusing a femtosecond laser, so a laser with very high or very short wavelength laser, or pulse rate, I should say. And if I have the correct laser spot inside of the diamond, if I focus it correctly, this is where the sort of research is. I can turn diamond into graphite. Right?
Okay.
So graphite is also carbon, so we can do that straight away. It's also conductive, like pencils are made of graphite and they're conductive, right? So we can change the material from its sort of stable crystal form to graphite conductive form. And so if we move the laser correctly, I can draw wires inside of the diamond, and that's where I spend a lot of my time doing. So
that's incredibly cool. Using lasers to make wires inside diamonds.
Exactly.
Basically.
And this is why it becomes interesting, because now we are free of the thickness of the diamond. So take it back to that sandwich thing. How close you have your electrodes is really important. So if we're restricted to how thick the filling of our sandwich is, we are then the charges that are safe if we have some radiation and it makes all of its electrons right in the middle. Those electrons and holes have to travel most of the full thickness, right? And it's really limiting in our design. But if we have freedom to sort of draw our electrodes as close or as far apart as we want, it means we can control the drift time of those charges. And bring it back to what you said about polycrystalline diamonds, so this cheaper diamond. If we can draw those electrodes so close together, it doesn't matter how good our material is, then we can use that cheaper material.
Okay, that's very cool.
Yeah.
Very cool. So these diamond detectors, are there any like applications for not just particle physics, so like I don't know, medical physics or anything else like that?
So what's cool about diamond again? So it's made of carbon. We're physicists, right? We can approximate people to be made of carbon. So we're all organic. So, taking silicon or silicon diamond as my example, silicon's atomic weight is around 14, whereas carbon 6, right? And the average, if you averaged a person or their tissue, it's 7, right? Or 7 point something. So 6 is a lot closer to 7 than 14, right? So when you're thinking about medical physics, so you're wanting to measure how a person's body would interact with radiation, having a detector that is much closer to a person than not means your measurement's going to be a lot better and you don't have to correct as much, right? Also, it's biocompatible, right? We're not sticking toxic things near people. Diamond, I could talk about this for a lot of time, but diamond also doesn't need as high a voltage to use and stuff, and we can use it in both directions. Like it doesn't have a polarity you have to use. So it means that it's safer potentially for people to use. Now there are already diamond dosimeters, dosimeter being the word for measuring dose in this sort of medical environment on the market that are used. But they're made with natural diamonds, which is also a bit crazy. They have to compete with jewelry makers.
So that must be more expensive than just the synthetic ones, which is crazy.
But because of the really high radiation tolerance, they are also used in nuclear experiments. So particularly, I think at ITER, they're putting some diamond pads around. Obviously, in high energy physics, we have an ATLAS experiment and CMS and BABA and KEC in Japan. Yeah, and then also tends to be used in sort of military atomic detection and stuff because they can't be destroyed. So,
sure.
Yeah.
Okay. So, do you have any like kind of advice for any students like kind of applying to university, maybe following your path, just for sciences generally or for physics specifically?
What I thought I would be doing when my experience at university, that I thought it would be when I was 18, 17 applying to university, it was completely different. Like the sort of roller coaster ride between modules and getting your exam results back is never what you expect. So this is, I can only speak of my experience, but I did very well at school, and so I thought I'd do very well at university. But then I got a lot of things wrong. I failed exams. I barely scraped through exams, and I'm still here doing a PhD. I think particularly in physics and physics at a good university like Manchester, there's a sort of fear about failure and getting things wrong. But actually, if you're going to do a PhD and you're going to be a real scientist, you need to know how to get things wrong.
Oh, exactly, yeah.
Yeah. So and when people are choosing PhD students, they prefer someone who well, this is general, and depends on the role, but they would choose someone who, say, got just about a first class over someone who got 100%, because every day in doing a PhD, you're going to have a problem. So that'd be my advice. Like, allow yourself to make mistakes and learn from them.
Okay, cool. And also, I guess, you wanting to do astrophysics at the beginning, just kind of be open to choices.
Exactly. So I thought I was going to do astrophysics because I loved looking at the space pictures, and that's what you see on TV a lot. But actually, the modules I ended up taking in my undergrad were mainly photonics and medical physics, which I'd never really considered. My favourite module I ever did at Manchester was the photonics and medicine in fourth year.
Okay.
Absolutely amazing course. It just blew my mind on everything that we're using. So we're talking about quantum mechanics, we're talking about chemistry, we're talking about photonics, obviously. So the module's called laser focused medicine. And it's all things that you'd have to understand a quite high level of physics. But we were discussing how it saved people's lives, and that was the first thing that properly captured my imagination for quite a while, and just wanting to be good at physics.
Okay. Well, very cool. Well, I think that's about time. So thank you very much. Do you have any questions for me?
Why are you doing physics?
I feel like a lot of physicists kind of are the same in that you can't really imagine doing anything else. So it's just there's a huge interest for physics, and I just kind of want to explore that.
What do you do? Can you give me a short synopsis of your master's project so far?
Yes, I can. So my master's project is also on Atlas.
I'm looking at Z boson decays, and Z bosons are very interesting because they're very heavy and they can decay into both electrons and heavy electrons called muons. So what's interesting about these decays is that you can use them to basically probe the accelerator itself and measure, for example, the effect caused by the crossing angle of the two beams inside of the detector.
Cool. Is that a lot of coding?
There's a good amount, yeah.
Nice.
Thank you very much.
Yeah, thank you very much. Thanks for having me.
Thank you.